The remaining sections of Chapter 7 in the ECE 301 workbook are concerned with inductance. We've already dealt with resistance, we've dealt with capacitance, and then the final major circuit element type we're considering, other than our voltage and current sources, is inductance. So an inductor can be created by coiling a wire, usually around some material, so that the current flow through the coil that you design generates actually a magnetic field. Michael Faraday discovered that in his law and presented that in one of the infamous Christmas lectures at the Royal Institute in London. The coil is usually composed of magnetic material, usually iron or iron oxide, and the iron cores are usually made in thin sheets, typically called laminations. So what happens is when the current changes in value, so now we're looking at the current changing as opposed to the voltage changing, which was extremely important to generate current in a capacitance. Now we're looking at how current changes and a resulting magnetic flux changes as well. Specifically, it's how we're going to get voltage. So Faraday's law of electromagnetic induction states that time-varying magnetic flux linking a coil induces voltage across the coil. So that's the key here, is how do we generate voltage across the coil? So for an ideal conductor, the voltage is proportional to the time rate of change of the current. So the constant proportionality now we're going to call L for inductance, as indicated here in the notes. And the polarity of the voltage is to oppose the change in the current. So what we have now, assuming PRC for an inductor, just like we would a capacitor, we have this equation. So remember, with a capacitance, it was current is the capacitance proportionality constant C times the rate of change of voltage. This is just completely swapped. Now the voltage is being generated by the change, instantaneous rate of change of the current. If the references are opposed to passive reference configuration, then like we've done before, you would add a minus sign to the right-hand side. The units of inductance are known as henries, represented by a capital H, and they specifically are volt-seconds per ampere. And the typical ranges for inductance are usually microhenries to tens of henries. So they're much larger than what you see with farads for capacitance. Over here to the right is the symbol, is the design of the circuit element. Notice the idea of coiling is represented by this particular design. And you have the current flowing in, and the voltage polarities are indicated here. And we again are representing it as PRC, that the current is flowing into the positive voltage polarity. So again, this idea of being able to store energy and then release it as needed, depending upon how current changes, as opposed to voltage, which was the case for capacitance. There is a fluid flow analogy like we saw before for capacitance. In this case, you can think of an inductance as sort of the inertia of a fluid flowing through a pipe, and assuming no friction. And the pipe has a constant diameter, so that means no distortions in the design of it. And the pressure differential between the ends of the pipe is basically this anomalous to voltage. So if you have differential pressures at the end of that pipe with the fluid flowing through it, that represents a different voltage, differential voltage in the circuit. The flow rate of the velocity is analogous to current. So the acceleration of the fluid, as you accelerate the fluid, the rate of change of the current would go up, all right? And you would then have more pressure. So as you increase the speed of the fluid through the pipe, you would increase more pressure, and therefore that is analogous to getting more voltage in the circuit. So the equations we use for inductances are indicated in the next little small section. How do you represent currents in terms of voltage? Well, give it an initial current, and you have the voltage as a function of time across the inductance. Suppose you want to know what the current is for a time beyond that initial point, T0. Well, given the fact that we've already talked about the fact that the relationship between the voltage and the rate of change of current is given by the standard representation of inductance with the proportional constant L, you can write di dt is 1 over L times V. That's just solving for that rate of change, right? Or you could multiply through I dt, and so that the differential in I is 1 over L times the voltage times the differential time. Therefore, you could integrate, and therefore, one equation you can get, if you needed to get the current exactly, you would integrate the voltage function, given that you know the initial current, and then you would integrate up to random, for any particular time t, you would integrate up to that, right? So if the voltage is finite, then the current function can only change by an incremental amount for a given time increment. So we assume that we have a very continuous function here with no instantaneous jumps in general, all right? So the key is, if you want to get current knowing voltage for inductance, you need to integrate. And then, of course, apply this 1 over L constant, where L is given in henries. What about stored energy? Again, you store energy. You can store energy in inductance from the magnetic field, just similar to the way you do it with capacitance, but the form is a little different. But we will go back, assuming PRC, we'll go back to our standard representation of power, which is just voltage times current. And so for an inductance now, we know that the power is going to be L times I of t times di dt, all right? Because now we have a representation of voltage here, right? Again, going back up, we know that V of t, just so we understand what we're doing, is L times di dt, okay? And for capacitance, okay? So if we just substitute that in, then we can represent the power completely in terms of the current itself and how it's changing. So the current function times its derivative, and we wouldn't need to know the voltage at all. If we assume that the initial current is 0, then the initial energy is 0, all right? That was kind of similar to what happened with the capacitance. If you assume no voltage to start off, then you have no stored energy. Here, if you have no current, you have no stored energy, all right? So suppose between that initial time 0 and then some later time t, you do get current, and it changes from 0 to a specified amount by some function of I of t, it depends on t. Then the current increases in magnitude, and the energy is delivered to the inductor and stored in the magnetic field. Very similar to how what happens to storing the energy with the capacitance between the plates. So the energy delivered then is, as we've always done, is the integral. The joules that you would get, you would integrate the power function. Now we're integrating this function, right? And then with the change of variable, you can show very easily that this is just going to be the integral of L I di, and then you can integrate that very simply as I squared over 2. So we have a function here of the joules would be given by 1/2 times the inductance proportionality constant times the square of the current, right? Which is different. We would have had the square of the voltage for the capacitance. Now we're looking at the square of the current to get the joules or the stored energy in the inductance. So that's the bottom of page 91. So let's flip over and look at a problem. We'll look at 2 problems, and then we'll try to wrap up the chapter here. So again, the energy is stored in the inductance, is returned to the circuit if you start changing the current. Just like what happened with the capacitance, once you started decreasing that voltage, then you released the energy to the rest of the circuit. That's the same idea that happens with the magnetic field. Once you decrease the current, you're going to release the energy to the rest of the circuit. So that the controlling parameter is current for this magnetic field-based element versus it was voltage with the capacitance with the plates, right? So this time, suppose we have a current waveform. Again, with the capacitance, you needed a voltage waveform, but now we're going to have a current waveform, and it should look fairly familiar. It's almost got the same shape of the previous problem we did with capacitance, but some values are different. We're going to ramp the current up to 3 amperes linearly after 2 seconds, and then we'll hold it constant for 3 amperes and then drop it back to 0 very quickly after 1 second, right? So the first thing we need to do, and we're looking at a 5 Henry inductance, so the parameter L is 5H, first of all. Just like we did for the voltage waveform, you should analytically define what the current function, 3-part function looks like. It has 3 parts because it has 3 changes. If the waveform has more than 3 changes, it's got more than 3 parts. So look again, slope, and you got the rise of 3 and a run of 2 for the slope. and it's a linear function, so 3/2 t is the first part. That is between time second 0 and 2, and then it goes constant at 3, and again, these are amperes. We can make sure we represent units there, between time 2 and 4, and then between 4 and 5. We have to be a little careful here. Again, the slope, it drops 3 units, 1 to the right, so the slope is going to be -3. Shouldn't take too long. The function that should work is 5 minus 3t, and that would be amperes. Again, you could check it. When you plug in, I'm just looking very carefully to make sure we've got the right values there. So the slope, again, in this case is -3, and we could use the point. Let's just go ahead and show how we get this. So the point that we can use is the t, when t is 5, y is 0. So again, the formula would be y minus y0 has to be the slope times this times t minus t0, where we have the point t0 or x0, depending upon how you represent the x-axis. That's the point on the line. And so what we should have is the y unit, the y coordinate is 0, so we'll have y is -3 times t minus 5, okay? And in this case, that should give us 15 minus 3t. And I kept thinking, yeah, need a 15 there, okay? So, and now we can double check. If we plug in a 4 into the t, we get -12 plus -12, but added to a 15 will give us 3. And then when we get time to time 5, we would get 0, which is perfect, okay? Again, that's just the point slope formula over there. So we're going to need the derivative. So it might be a good idea to go ahead and represent what the derivative would be, because we're definitely going to need it for the voltage function. So if we go ahead and take derivatives, clearly we'll get just 3/2. It's a linear function, so the derivative is constant, and that will be true for time 0 to 2. That's a constant function for the current, so the derivative is 0 between 2 and 4. And then finally, the only term that you're going to have, the term that's going to produce a value is going to be the -3t, because derivative of the 15 is 0, so you should get a -3, right? Again, just basic calculus there. Fine, good. So now we've got all the derivatives we need. So then we can go ahead and represent the voltage function, and we'll draw them as we go through. Just remember the formulas. It's the inductance times the derivative. And again, 3-part function. You'll take this derivative over here and multiply it by the 5 henries. And so you'll have 5 times 3/2, or 15 divided by 2, or you'll have 7.5 volts. Again, keep all the units in henries, just like we kept everything in farads before. So just keep the units in henries here, okay? And this is true between 0 and 2. And then, of course, you get no volts because of the derivative being 0 there. When you don't change the current, you have no voltage, right? So with the magnetic field, you must be changing that current to keep that magnetic field absorbing energy. And then finally, you'll take -3 and multiply it. Excuse me, -3 times the 5 will give you -15. So we'll have -15 volts between 4 and 5, okay? So let's go ahead and just sketch that curve off to the side here, just so we have an illustration. It obviously is going negative much farther than it is positive. So when you draw your graphs, we might take that into account, that we need to draw more room below the x-axis or the t-axis in that case. We'll stay in seconds, okay? So time 0. Remember, we keep the same time unit and the same, basically the ticks as the waveform that was given, because those are the time periods we're interested in, okay? So, so in this case, the highest it's ever going to be is 7.5 volts. We're drawing v of t, but it's going to drop twice that length down here, and we'll put that -15 for the volts there. And so just sketching across here so we can see how high or how low we need to go. What's going to happen, it's constant between 0 and 2. And so maybe I'll change colors here to make it a little bit more obvious. So here we go. From 0 to 2, it's there. Then it drops to 0 between 2 and 4. And then what happens below, it drops right to -15. And then stays there to 5. We don't, we haven't gone farther than 5 because we're only given a current up till 5 seconds, right? So kind of snaggletooth there, right? For the voltage, right? Voltage on, voltage, positive voltage, negative voltage. Rate of change of current is positive, rate of change of current is negative. So that matches up logically. Let's go ahead and do the stored energy. All right, so let's do WT using our new formula, 1/2 the inductance times the square of the current, okay, and represent that function. So we're just going to square this there and multiply by the 5 henries and divide by 2. So if we do that, we're going to get 5/2, right, times the quantity 3/2 T squared, and we could simplify that as 45/8 T squared, and this is joules, and this is between 0 and 2. And the next one is just 5/2 times 3 squared because it's just constant, and that's just going to be 45/2 joules, and that's between 2 and 4. And then again, that one down there is going to be more complicated, but I recommend just leaving it because all you're going to do is plug values in to get the curves out. So I would just leave it in the form 15 minus 3t squared. I think I said that earlier for capacitance. There's no need to factor that out. Just leave it in that form so you can evaluate it easily. And then again, that's joules, and that's between 4 and 5, okay? And so one thing that I hope you notice immediately is you're getting quadratic functions. So is there any way that that's ever going to be negative? No. So the energy you're storing is going to be positive. That makes sense. There's no such thing as a negative joule anyway. So this matches up beautifully with our logic. So let's go ahead and draw this curve maybe right underneath the voltage curve. And it's going to be strictly positive. So we'll let's make our t-axis first. Oops. And then we'll draw in our y-axis here. In this case, this axis, we are drawing the joules, so WT, our energy, so this will be in joules. And go ahead and mark the tick marks of time. 1 second, that was 1 second there. 2 seconds, up to 4, and then 5, okay? Right? And then all we have to think about is what's the largest value going to get out of all these functions here, okay? And it's going to happen very quickly when you get to 2. When you plug in 2 squared there and multiply 45 divided by 8, you're going to get about 22.5 joules, right? I'm not drawing it to scale here to match the other one, but what's going to happen is you're going to hit that in a quadratic way. So we'll draw a shape of a curve that looks like a quadratic. And then it's going to be, this is the value that's going to match it here. It's going to be constant at that 22.5 through the 2 seconds, between 2 and 4 seconds. And then it'll drop down to 0. It's a steeper curve, but it's also quadratic. So it's kind of skewed there. So it looks kind of like a volcano, but it's not symmetric clearly because this slope and this slope are not the same, okay? Right? So current, the rate of change of current goes up. You're generating you generate the energy. You stop changing the current, right? Again, it's constant. Current, you hold the current constant, you hold the energy, then you start decreasing the current, and you release the energy, okay? That's how the logic matches up, right? Last thing I like to do is the power, P of T. We could get this by, again, we can use we don't need the voltage, we just need to multiply the current with its derivative. and then the 5 henries with it, okay? So this is a little bit more complicated, so we'll just leave some space here. So we'll have 5 henries times the current function, which is 3/2 t. Then we multiply by the 3/2, which is the derivative. And that function should turn out to be 45 t over 4. And this is watts, okay? This is between time 0 and 2. And then again, let's do the same thing here. 5 henries times 3 amp current, but 0 rate of change because you held it constant. So that gives you no watts, okay? So you have no power. That's no problem. We're storing the energy. We have no power, okay? And then finally, 5 henries times the current function, which is decreasing, times its instantaneous rate of change, and that was -3 up above. And cleaning this up a little bit, you could write this as 15 times 3t minus 15 watts between time 4 and 5. Okay, right? So this will look very interesting because what we'd like to see is this is very, these are linear looking, but notice they have really large slopes. So these are going to generate spikes. So these watts are going to be spiking, okay? So we're going to get positive and negative values. So we'll sketch our curve here underneath the stored energy and allow it to be negative. In fact, it's going to be much more negative than positive. So I'll kind of leave myself some more room here. Nothing has changed on the time axis. So mark your time. Again, that initial waveform is dictating these benchmarks where we're looking at each of these parameters. We're drawing the power function and the scale as watts, okay? So what happens here is the peak, if you start ramping up to 2 and you plug into 2 and see what happens. In this first part of the function, you plug in 2, it'll come out again to, interestingly, 22.5 watts. Okay. And so we'll scale that. We'll just draw that across so we can see the value again. So it's linear. So what happens is it looks like this, and then it drops right back to 0, okay? Okay, so this is definitely a linear function. So if you plug in 2 there, you're gonna have 45 times 2 divided by 4. That's 90 divided by 4. That's clearly what that value is. Then it's stuck at 0 for the next 2 seconds. And then you plug in 4 into this, and you can see really quickly, you're going to get -45 out here. So I'm going to bring it all the way down here. How do I know that? Again, plug in 4 there, you're going to get 12 minus 15 is -3 times that, right? So you're going to hit that -45. So this is going to jump straight down here and then find its way all the way back up to 5 in a linear way, okay? Right? And so what we can annotate this with is this is where this spike here in this power is due to current increasing. So you will get these positive peaks on an increase, and then you're going to get this jagged drop here when the current decreases. And the severity of this depends on the severity of the change of the derivative, right? So if it's a very gradual decrease, right, then it won't be such a quick, you know, it'll drop, but it'll be a gradual decrease back to 0. Or this is very fast. It's very fast. This has to do with that particular waveform, okay, that you had. Notice this is a quick drop off. This is a quick return to 0, okay? So this is a really nice problem, sort of summarizes everything that you will have with inductance in terms of being able to take a current waveform and then generate all the other 3 important parameters for inductance, right? So that was the bottom 92. Let's do one more problem before we summarize inductances in terms of their series and parallelism. So this example 9 on the page of 93, we have the switch we have a switch on a circuit that's got an inductance with a voltage source of 10 volts. And so the idea is when we close the switch at time 0, that gives us a connection between the 10 volt, not course, that should be source, so we'll correct that in our notes, and to the 2 Henry inductance. So we want to find the current that's going to be generated through that inductance, okay, as a function of time. So the voltage applied to the inductance is finite, so the current should be continuous, right? And prior to time 0, that current is 0. In other words, there is no current flowing through there because it's an open circuit there, right? So how do we produce the current? We'll go back and say, all right, we know that to get current, we have this equation involving an integral. It's 1 over the inductance parameter L, integrating from T0 to T of the voltage as a function of time dt plus whatever initial current we have, okay? So we've already assumed, because the switch there, that this I of T0, which will be I of 0, is 0, right? That was our assumption, that you don't have any current to start with, right? Okay, so we know that L is 2 Henries, so that was given to us, right? So all we need to do is represent what voltage would you, these two will be in parallel. They'll share the 10 volts. So therefore the current would have to be 1 over 2 times the integral from time 0, initial time, to T times 10 dt, right? Plus 0, which was the initial current. And that's just going to be 1/2, right? Times 10 times the integral from T dt, or that's just 5, right? Integral T dt. And I think you can do that very quickly. So that's just going to be 5t evaluated at t and 0. And when you plug in t again, that you're just going to get 5t, right? So it's linear. It's 5t amps, okay? So what would happen then is just sort of illustrated in time. We draw a little curve here, time in seconds. And we started with 10 volts. You could draw both curves if you wanted to on top of them. Say, let this be unit 10. This will be 5. Then what's happening is 1 second, 2 second. First of all, the voltage isn't going to change. So the voltage is going to be this constant function here. So that's what V of t looks like. It's an independent voltage source, which isn't going to change. But what's interesting is, well, we start with no current, right? And then after well, first of all, we can get a data point here. If we plug in time 1, we get 5 amps. So that's a data point. But by 2 seconds, we're already matching the voltage, okay? So this is an illustration of what I of t looks like. I of t is 5t, okay? And that'll just keep going on and on, all right? As you increase the time, it'll be a linear increase in the current that is being generated through that inductor, okay? Right? Now, interesting enough, if the switch, if we go below here, the same problem, if the switch was opened at 1 second, right, the current would fall to 0, right? So for an abrupt change, in other words, you know, someone just accidentally flipped the switch and it was off after a second, that would be a very abrupt change. And typically what happens is we think of infinite voltage would be inferred across the inductor because it's so quick, but it could only last for an instant. So, and then the current would start falling. So when you have very large voltages, they can appear when you switch circuits containing inductance. In other words, when you flip switches on and off, you still can have voltages appearing. That's what this is saying, that you don't get the, you know, yes, when you open it up, the current will go to 0, but there's still voltage flowing across here. So you have to be careful, right, sometimes. For this particular circuit though, opening at times after 1 second, you know, could create a high voltage or an arc across the switch contacts. The arc persists until the energy in the inductor is used up. Not a good idea to keep flipping the switch back and forth, because that'll ultimately cause a lot of residual damage in the circuit because of maintaining higher than expected voltages through the life of the circuit, okay? All right, so last couple of things we're going to talk about is what's the relationship between these inductance in series and parallel. This is an illustration of putting them in series. Should look very familiar to resistances. Yes, these are not the same as capacitance. These are the same as resistances. When you put them in parallel with the same current flowing through them, to get the equivalent, you add them. So L's act like R's, not C. Then on page 94, then you probably guess, yeah, if they're in parallel, then you need to use the same approach we did for resistances, okay? The reciprocal, the sum reciprocals, or take them 2 at a time and do exactly that same product sum ratio formula we did for resistances. And finally, in terms of practical inductors, if you had like, this is on the last thing on page 94, if you had about a 1 microhenry inductor, that, just to give you an example, it took about 25 turns of a 28 gauge wire using iron oxide, and it's sort of a donut shape, which is exactly the shape that Faraday used to demonstrate the very first electromagnet. And suppose the outer diameter is about 0.5 centimeters. A 5 Henry inductor could be several hundred turns of an 18 gauge wire, having a mass of 1 kilogram. So just to give you an idea, this is relatively small and simple, and this is huge, okay? So metallic iron forms called cores, again, we talked about laminations, are typically used to build these things. Sometimes though, voltages can be induced by the changes in that magnetic field, and these are called eddies or eddy currents that flow in the core, and they cause energy to be dissipated, lost, okay? So usually core loss of energy is not heavily desirable, all right? And you'd like to, just like an insulator, keep things in and not lose this energy. So again, like we had before with capacitors, it might be a good idea to model a practical inductor that demonstrates some of that loss of energy due to eddy currents, okay? So like real capacitors, real inductors have parasitic effects. And over here on figure 18 is a good example of how to use resistances and even a capacitance to model the effect of these eddy currents. The capacitance in this case represents what's called interlining capacitance, and it's used to actually represent an electric field in the dielectric and the inductor, okay? That means that you'll end up with plate-like action in the insulator between the coils of the wire. In between the coils of wire will actually act like a little bit of a capacitance. And so what they do is yes, here is your ideal inductor, but to represent the loss of energy, put it in parallel with the capacitance and what represents the loss to the eddy currents over here. And then maybe a loss due to the lack of perfect superconducting material property, and that be RS, okay? So that's just a typical thing that might be more effective to model, because it would take into account that in the reality, you're not getting all the inductance that you thought you were. And that will ends up in chapter 7, and then we'll be moving on to the final chapter of our workbook on putting together RC circuits, or specifically first order RC circuits in chapter 8.